So here, we have pure sig figs. This one. The rules for sig figs is we're only allowed one guesstimated digit, and so this is 28 milliliters, which means the guesstimated digit is 8, and so we're estimating that 8. Is that correct? We're estimating the 8 here. Yeah, that's correct. And so this would be a proper measurement, 28. If we go to a higher, what do we call this? A higher precision or a higher accuracy instrument? What do you call it? Higher precision or higher accuracy? Or? It turns out we call this a higher precision. That is, it's more easy to be more precise with this. Precise means, how much variation, how wide is the uncertainty range. So if it's a narrower range, then it's more precise. If we look at this measurement, then we aren't guessing the 8. Did we have to guess the 8 here? Is the 8 guess? No, the 8 is for certain. This is for certain 28, right? What we have to guess is between 28 and 29. Well, how far? And so what we do, as always, is something you probably did with the other one. Let's see if I can find on the right here. So what we do is we draw these imaginary lines in our head. So there's a halfway line, that would be 25. So this would be 20, then 21, 22, 23, 24. 25 is midway, 26, 27, 28. So we say this is, to me, I would have called this 27. But, this the uncertainty that's there anyway, but it's okay. Oh, the same thing here. What we have to do is we draw in our imaginary lines, so that this is how we're going to estimate the estimated digit here. Is there a 0.3 line here? No, there's no 0.3 line. What they're doing is they're just guessing it's 0.3. So I have 28. If it's right on this line, we call it 28.0, right? And then just above, we'll call it 28.1, etc. To halfway, I'm going to call it 28.5. So I'm going to have 5 lines here, 28.1, 28.2. I would have called this 28.2 myself. Because it looks like the halfway mark there, it's closer to the start than it is to the finish. So that's why I would say 28.2. But, whatever you do, be consistent with the way you measure things. 23, 4, 5, 6, 7, 8. It's the estimated digit. So we're allowed to estimate that one. We get the proper recording at 28.3. Here we don't have to guess the 28.3. This one we're reading from the top down. That is, we're draining. Do you see on the bottom of this, there's a little valve. The valve's called a stopcock. We can open it and close that to drain fluid. And this one we can just figure out how much fluid has been drained out the bottom of this. And so it's going to increase as we go down. So we see 28.1, we see 28.2, we see 28.3. So 28.3 is certain. So it's between 28.3 and 28.4. And so this one looks to me to be halfway between. I would have called this one 28.35. Because it looks like it's halfway between 3 and 4. Here's 28.30. 28.40, and actually no, I would say 28 halfway would be there. I'd call this 28.34. Let's see what they call it. They called it 28.32. So it's hard because these are not actual pictures of the measurements, so it's hard to tell based on the perspective that they're trying to show perspective in the drawing, and it's hard to tell if that's a meniscus or not a meniscus.
So all of these images are measuring the same amount of liquid, it's just with different levels of precision.
Correct. You know, people pay big money for high precision instruments. High precision instruments can give you, you know, each time you can locate it precisely. You know, versus low precision instruments, it's gonna one time it's here, the next time it's there. You know? And so there's a great deal more fluctuations in the measurements with lower precision instruments, higher precision instruments. The same thing with this. You know, we have two rulers here. They're the same. These rulers are measuring inches. Although the bottom ruler, I've never seen a ruler that measures in tenths of inches. I mean, it would be good to measure in tenths of inches. That way we don't have eighths, sixteenths, 32nds, 64ths. You know, but these are 2-inch rulers. The top one we'd call low precision. You know, if you gave the top one to different students and have them measure it, you know, you're going to see a wider range of values than if you gave the bottom one to a classroom full of students and have them measure it. There, it will be a much tighter range. But can you record what's the top measurement there? What would you call that? 3.5, like midway between 3 and 4. That's hard to see because, like I said, these drawings are really hard. Okay, it looks like the end of the leaf is about there. Does it look midway?
No. It's really 3.4.
All right, 3.4. All right. Well, whatever, you put it down. And then the bottom one, they didn't line it up, so they put it here. And it looks like it's 1, 2. It looks like it's just a little bit past the 4th line here. It's a little bit past the 4th line. The second, you would think it's centimeters because I've never seen an inch ruler like that. But according to the instructions, both are inch rulers. And so I've never seen an inch ruler that measures a tenth of an inch.
So you want us to record both of them?
Yeah, record both of them. Alright, did you guys get the recordings? Yeah. Alright, can I have those cards? I just want to see what's this. Thank you. This is just so I know how much time to talk on this stuff. All right. You know, I have to watch out because sometimes I'll have a mental bias. Like, for example, this morning I called the top one the inch ruler. Maybe it's a centimeter ruler. But the bottom one I definitely called the centimeter ruler, just because I know what centimeter rulers look like. That's what it looks like, right? Although they said it's an inch ruler, calibrated in inches, so I would have gotten it wrong. You know, I would have put centimeters rather than inches. So we have to be careful because the same thing here. You know, normally when I think about the lines, the graduations here, I think in terms of tenths. You know, we go 3 to 3.1 to 3.2 to 3.3 to 3.4. So I would have said, okay, that's 3.4, and then it's right on the line, so I'd call it 3.40 to indicate it's right on the line, not above the line, not below. But when you look at it, could it be 3.4? Is that possible for that? No. And then you go, well, that's a crazy graduated cylinder because it's all in 2/10. So the first line's 3.2, then it goes 3.4, and then 3.6. And I've never seen a centimeter ruler, I mean an inch ruler like that, but I have seen graduated cylinders like this. In fact, our lab used to be filled with graduated cylinders like this. I think, fortunately, we've gotten rid of all of them. Never really liked these ones that measured in 2/10. And so I think your 10 milliliter graduated cylinder measures in 1/10 of a milliliter increments, which is the standard. This 2/10 is bizarre. But anyway, what we would do is we do the same thing. You know, the next line, that line is 3.6, the next line above is 3.8. And so we have to guess that digit. Well, what digit are we going to guess? We're going to guess the 100. So this says right on the line, it's 3.6. There's no guessing there. It's the 3.6 line. And so we're allowed one guesstimated digit. It's got to be 3.60, milliliters. So this one is a very tricky one. This one here is the same. It's 2/10. So there's 1.2, 1.4, and it's just slightly above 1.4. So, but you know, how much? Well, normally we have a 1.5 line. And so doing these, you know, it's kind of tricky because in a way you're guessing two digits, especially when you get closer to the center or if you're marking. But we would have to mark, rather than 10 imaginary lines, we'd mark 20 imaginary lines and then see which one it lines up with. 20 starting at 1.4 going on with 1.6. 1.41, 1.42, 43, 44, all the way to 60 would be that. Now, some of these are just not what you typically see. Let's see something more of what you typically see. What you typically see is something like this. This would be like a 50 milliliter garage cylinder. There's two scales here. One is just the total volume. The other is, you know, if you start off at 50, and then this one reads how much you drain out the bottom. Although we don't drain out the bottom, we pour it off the top. So we might have started this at 50 and then pour it off, and then measure how much we pour off. But anyway, we're measuring the volumes here. So what we're going to do is we're going to go from the bottom up. I think. Yeah. And so what would this top measurement be there? Yeah, top one. The top one is overfilled, and so you can't have much certainty in that measurement. Right? So you know, the top one for me, I would just write greater than 50, maybe between 50 and 60 or something. You'd have to indicate in some way that it's highly uncertain, that top one. What's the second one from the top?
So
48.6? Yeah, it looks like it's just above the halfway mark, you know, the valley there. Do you see that? And so 48.6 looks good. 48.6. It's between 48 and 49. How about this one? This one's between 36, 7, 38 and 39. What do you say? For certain it's 38. Now we have to guess. 38 point, yeah, 1 or 2. You know, 38.1, 38.2. Just like that. It depends on where you mark it too. If you're measuring right at the base or right in the thick of the meniscus, you know, it would make a difference in measurement. Okay, how about this one here? Well, this one they got 28.3. Would you agree with that or disagree? There's 25, 26, 27, 28. This is 29, so where is it between 28? You agree? No? What would you get? 28.2? Okay, you're probably measuring it off the bottom here. They're probably measuring it in the middle of the meniscus. That's probably the difference there. myself, as far as personal, it depends on how thick the meniscus is, you know, but usually I'd go off the middle of the meniscus, because normally the meniscus is pretty thin. So, but these are very thick menisci here. That's going to play a factor in this next one. This next one, you measured right out the bottom or the middle of it. If you measure right out the bottom, then it looks like the bottom is right on the line. Now, do you measure it in the middle of the line, or the top of the line, or the bottom of the line? You would measure it in the middle of the line. So it looks like it's right on the middle of the line, which would mean it's 21, 22, 23. And since it's right on the line, you call it 23.0, indicate it's right on the line. But if this one, it depends on the line too, because you know, if there are more lines, it could be, you know, more decimal places out. But if you measure it right in the middle of it, then it's just right above. So this might be 23.1, or might still be a 23.0. But you know, that digit has some uncertainty, so it's okay. You know, it's not. Sorry. And so this sheet is from your lab manual called Measurement 4. Measurement 4 just gives you additional practice measuring certain things. And so let's take a look at one of their measurements that they took. Now this is mercury. Mercury hates glass. So if you look at mercury, which would be inside the tube here, is trying to avoid touching the glass, and so forms a concave meniscus. So we measured at the peak here, rather there's no valley measured. So we measure at the peak, and here we just measure at the very top of the peak. Makes sense. But measuring at the very top of the peak, would you agree this is 0.35? So if I look at it, this is 0, that's 1 degree C up there, so this is going to be 0.1, 0.2, 0.3, so it's between 0.3 and 0.4. Looks like it's right in the middle, so 0.35 looks reasonable to me. Looks like a good measurement. This is a lower precision or a higher precision thermometer than the last one. This is a lower precision thermometer. The last thermometer we could get to the nearest hundredth of a degree. This one we're only going to be able to get to the nearest tenth of a degree, because if we look at the markings here, this is 40 and 41. And so it looks like it's about halfway between 40 and 41, which means it's 40.5. I would have called this 40.5. They call it 40.4. So it's close. All right, so these are measurement practice problems, which we want to get in chapter 3, is measurement. So let's take a look at some other practice problems. Is anyone doing this, looking at the end of chapter problems? The blue ones? So let's take a look at this. How many, what would that count as correct?
It's like, you know, like,
Oh, how much variation in the answer would I accept? You know, as long as it's close, that I can see it looks reasonable, then you're okay. If something's pretty far off, like for sure, you wrote 30 point, let's say you wrote 30.5 or something like that, which would indicate it's halfway between the line, but it was clearly biased towards one side or the other. That's reductive. Normally what happens is people write the wrong degree of precision. That's more significant error than just making a slight there. All right, so what we want to do is we just want to kind of take a look and see, what types of homework problems there are. I know there's already Newton. I know Newton does scientific notation, but you could also do some here. So for example, write the following numbers in scientific notation. What would the first one be? Yeah, 3.22 times 10 to the negative 4. If you make the number bigger, so we're going from 0.000322 to 3.22, we're making the number bigger, the coefficient bigger, we have to make the exponent smaller, so it's negative 4. How about B? B, we're going to make the number smaller, the coefficient smaller. Therefore, we have to make the exponent bigger. So what would it be? Yeah, 6.03 times 10 to the 9. C. Yeah, 6.19 times 10 to the negative 12 is correct. Good. You know, you go through problems like this, and if the problems seem kind of routine, that you have a good grasp of the material, then you skip ahead. Just skip ahead. Skip ahead. Then, we skip ahead. There's some big problems, some other calculations. And we see another section, conversion factors. This is a problem I didn't know the answer to. What is the mathematical criterion for two quantities to be equivalent? And so I was thinking, mathematical criterion, is that something that's precisely defined, or is that something that's loosely defined? And so I wasn't sure, so I Googled it. But then I was thinking, why Google it? Because, I have the answer. Equation? Invert? Oh, you can invert the conversion factor equations, no problem. But what is the mathematical criterion for two quantities to be equivalent? I don't know. So what I was thinking was, I'm thinking they're talking about exact equivalency versus approximate equivalency. So I was thinking like 1,000 milliliters is exactly a liter, right? Versus 3.785 liters, is that exactly a gallon? No, so I was thinking something along those lines, but then I thought, why waste your time? And you shouldn't waste it. You should just look and see, in what kind of context they're thinking. And they have the answers to the blue problems here. So then we come up with this. Two quantities x and y must be related in the form y equals mx plus b. And then that threw out more questions. I just have no idea what they're talking about. Because when I'm thinking about a conversion factor, I'm thinking about, 1,000 milliliters is equivalent to a liter. That's a conversion factor, right? And then I can invert it. This converts it from liters to milliliters. If I invert it like this, 1 liter is equivalent to 1,000 milliliters. This converts it from milliliters to liters if I'm converting numerically. There. So in the context of y equals mx plus b, I wasn't sure what they're talking about because, I spent some time talking about dimensional analysis, straight conversion factors versus algebra. Y equals mx plus b is an algebraic equation. Y equals mx plus b we have to use because we can't come up with a simple conversion factor. So, for example, degrees Fahrenheit is equal to 9/5 degrees C plus 32 degrees. That's not what I call a conversion factor. That's what I call an equation to solve for one or the other. However, temperature, we can use a conversion factor. We can use a conversion factor for temperature, which is 180 degrees Fahrenheit is exactly 100 degrees C. You know, this is a conversion factor. But if these two are two different things. You know, one of the things you do is you go back through the notes and you look. This one's for just determining the temperature. This one is not for determining the temperature. This one's for determining what? This is part of the pattern, this is part of the pattern, but this one's for determining delta T's. And so this one's for T, this one's for delta T. But they're equivalency in that sense that, you know, then I was thinking, okay, you know, this could be it too. But the thing is that, you know, for me, how do we know? Well, this is by definition. The others are by measurement. And so we can know the equivalencies either by definition, that is, somebody defined it that way, or by measurement, that they're equal. But, you know, when we're coming up with y equals mx plus b, you know, if I have 1 liter here, that's equivalent to 1,000 milliliters. So I can come up with an equation for that line like this. You know, it's 0 milliliters, we'll have 0 liters. But, you know, how do I get these data points here? 0, 0, and 1,001? That has to be by definition. Otherwise, you know, I'm not going to have any data for that. And so, anyway, it didn't quite make sense, so I'm not going to dwell on this particular problem much longer, except just to kind of ignore it. I'd like to take a look at its sister problem to see if I can figure that out. And so let's go 13 and 14. 14 is a similar problem. 60 seconds and 1 minute are equivalent quantities. Explain why this is true. You know, my explanation is they're equivalent because that's how it's defined. You know, they're equivalent by definition. Somebody defined 60 seconds as 1 minute, or 1 minute is 60 seconds. Fortunately, the book didn't give an answer for this one, so I'll just go with mine. The correct answer. Otherwise, I'd hate to see the answer. Because how are you going to put it into the context of y equals mx plus b? Well, that, you know, it happens. Sometimes, I'll tell you, you know, what happens is these problems take a long time to write and the answers too. So oftentimes they're outsourced to various people, you know. And sometimes the answers are inconsistent. And then it happens. Write the equivalency for each conversion factor. I mean, I would say 3 feet is defined as 1 yard, or 1 yard is defined as 3 feet. Is that right? Okay, so let's take a look at 15, since I want to make sure I'm kind of on the right track. I would have written it a little bit differently on the answer here. If you look at number 15, they said 3 feet equals 1 yard. I would have just said 3 feet is with a triple bar defined as 1 yard. Okay, these are, now I'm getting it, what they're getting at. But sometimes it requires additional clarification. All right, what do we use these conversion factors for? We use these conversion factors to do simple conversions like this. How long will it take to travel 406 miles between Los Angeles and San Francisco at an average speed of 48 miles an hour? And so here, 48 miles an hour, we call that a relationship or a conversion factor. And 406 miles is our given. So, you know, a problem like this, we start off with 406 miles. Miles I'll abbreviate MI. And we're going at 48 miles per hour. The miles cancels, miles leaves us with hours. Now we have to worry about sig figs. Now with sig figs, there are always issues with the sig figs. And how many sig figs are we allowed in this answer? 3. 3 is incorrect. 2. 2 is correct. Do you see why I got 2 sig figs allowed in this answer? From the miles per hour. It's only the 2 sig figs. And so multiplication and division, we look at the fewest number of sig figs and our answer should contain the same. So we have 3 sig figs in our given, 2 sig figs in our conversion factor. This is why, you know, I like conversion factors that are more precise than the given. And so my usual rule is if we're given 3 sig figs, then we should have 4 sig figs in the conversion factor. But unfortunately, in this case, the miles per hour is just some average, and it's not so precise. You know, did they drive right at 48.000 miles per hour? Do you think, or just around 48? Yeah, just around. So anyway, the answer comes out. Now, what I want you to do is I want you to always show more digits. So I got 8.458 hours. And so we're going to round this to 8.5 hours. 8.5 hours. You know, and this would show the degree of uncertainty, because if you say 8.5 hours, you're talking anywhere from like 8.45 hours to 8.54 hours, you know, in that range. But if I said 8.45, you know, it's a much narrower range. And if I said 8.458, you know, that's going to be tough. They did it in that kind of precision. And so those are our conversion factors. Now, with sig figs, we have to pay attention to the rules for sig figs. Now, for the rules for sig figs, we have 2 sets of rules. We have multiplication, division, and addition and subtraction. And so what I want to do is I want to do a, actually, I don't want to do addition and subtraction just yet. Let's get some practice here. Let's go for the so that's a 1 or 2 step conversion. You know, 1 or 2 step. The thing is, you know, we did some pretty hard problems yesterday. Not yesterday, was it the day before? Thursday sometime. We did some pretty hard problems. So a student came up to me in the morning and asked me, should they study Chem 1A level problems or should they study Chem 4 level problems? But, you know, obviously Chem 4 problems. But the situation is that when you look at those Chem 1A problems, were they impossibly difficult? No. You know, the only difference between a Chem 1A level problem and a Chem 4 is you have to add more conversion factors. That's it. There's no other difference. And so you know, when I think of the difficulty level, I don't think they're different. Chem 4 and Chem 1A and dimensional analysis is the same. I think a Chem 4 student can get any Chem 1A problem given enough time and access to all the conversion factors. Basically. Well, let's pick up I want to take a look at the hardest Chem 4 dimensional analysis problem. The hardest will be number 128. Number 128, you calculated that you would have to work 6 weeks. Okay, so they gave an example, 3-29. I'll show that really quick. Unless, 322. 27. I forgot to read this in the morning. Suppose that you have just landed a part-time job that pays $9.25 an hour. When was this book? $9.25 an hour was 2016. You will work 5 shifts each week, and the shifts are 4 hours long. You plan to save all your earnings to pay cash for a 50-inch 1080p smart plasma HD TV that costs $1082.49, tax included. You're paid weekly. How many weeks must you work in order to save the money to buy the television? You might also be interested in knowing how much cash you will have left for video games or other goodies.
Or are they good?
I don't want to know how much cash. You know what? You're gonna work this job and then you're gonna quit. Even if it's midweek, you'll quit. So if it comes out to 5.25 weeks, then stop there and you're going to be prorated to pay. We are not going to figure out how much extra. Although the extra is useful. No. So do you want to do this one or do the challenge one? Let's do the challenge one. The only difference between that example and this example is that example, you got to take all your pay, all $9.25 per hour, to put towards the TV. Unfortunately, your take-home pay is not that much because you're going to have withholdings. And so what they're saying is you're going to have exactly 23% of your earnings withheld. And so unfortunately, it's going to take longer to pay off the TV. And so can you work on this? You can work with your neighbor, your friends. But work on this, but we need another survey. Can you work on this on this shirt? One of these boards?